Moriarty in the back. Rick said I kind of led the effort at Skaneateles, but really Vince and I co-led it. And in terms of the deployment of the sensor platform. Let's see if I can get this going here. And certainly none of this would have
Is that
happened.
Staghorn Cliffs?
Sorry?
No, I was just commenting on the cliffs
Yeah.
and the.
We're good. Thanks. Okay, so I'm recycling this picture. Several of you were at a couple of our presentations back in the late summer and fall of 2018. Hopefully not too much of this is a review of that. But I'm going to come back to this picture. I think it's pretty interesting for a couple of reasons. We'll get started here. So really, we were deployed for all of the confirmed blooms in 2018. We deployed on July 30th, and we're there through October. What's interesting here, if I'm reading the numbers correctly, they were all at the north end except for that one. And I've been looking at that one pretty carefully lately. And we'll come back to that. Spoiler alert. I'm going to be a bit of a contrarian. I'm going to make the claim that based on our findings, all of the blooms in 2018 were actually driven by internal loading, not hypoxia-driven internal loading, but internal loading driven by hydrodynamically driven mechanical forces. So right away we realized, well, there's a big internal seiche. For anybody that doesn't know, the lake stratifies in the summertime, warm water at the top, cold water at the bottom. That thin layer in the middle is a thermocline, and that gets displaced during a strong wind event, and then when the wind stops, that rocks back and forth, and that thermocline is a density gradient, and that actually disturbs the bottom. There's really nothing new there. Some great literature on it on the web. We saw these exact phenomena in our data, and we also saw it in our three-dimensional hydrodynamic modeling. This is actually a screenshot of vertical diffusivity, and essentially you can think of that as a type of turbulence at the lake bed. So that's a map of the lake bed there. We'll get back to that. Our deployment location, by the way, is that little green circle there over on the right. I have a pointer here. Our deployment location was right here. So just to bring home the point that the seiche disturbs the lake bed, this is ADCP velocity data, and the seiche downwelling and upwelling is revealed in this blue to yellow transition here. This is a temperature profile, and this is turbidity. And so we see when the upwelling comes in, we get stuff off the bottom. We also had acoustic Doppler current profilers on board. This is acoustic backscatter, and we can also see stuff exploding off the bottom there. So just to wrap up this notion of the seiche, we think that we more or less know that the driving force of this seiche was a relatively strong wind event on August 1st, south wind. So that displaced that thermocline, and then that was released late in the day. And it led to these oscillations. It's like a clock. Skaneateles Lake is a big clock, and it ticks about once every 23.4 hours. And so here's the driving wind event. In the absence of anything significant after that, this clock went on for about 2 weeks, undisturbed. And it's a testament to the periodicity of this lowest frequency slosh back and forth. And because of the purity of this wave here, we think that this wind event, and we corroborated this with other weather data, was really the strongest, most coherent wind event of the stratified season. And so we think this is really the first significant seiche of 2018. The first confirmed blooms were on August 4th, 5th, and 7th. I consider that to basically be a single bloom. What's interesting, it's not shown here, but the turbidity disturbance at the bottom kept going for that whole 2 weeks. But we did not have HABs after August 7th. So the seiche we think is a driving component, but there's something else. And this is just an interesting thing here. Finally, we get another south wind, and it modifies, it alters the angular phase of this wave. And then after that, all bets are off in terms of the periodicity of the wave. The other thing I'll mention here, because of our assumptions that this was the first significant stage of the season, we were able to actually predict the first HAB on Skaneateles Lake of 2019 to the day, using our Deep Thunder weather model. About 7 days earlier, we saw a significant south wind event approaching, and as that actually happened, and then we saw, I won't spoil too much, but then we saw other conditions that the day before, on September 2nd, we sent around some emails and I said, watch for a HAB tomorrow. I actually forgot about that, sending that email out. I was on vacation, and a couple days later, I think Rick, you sent an email that Skaneateles had their first harmful algal bloom of 2019. So you had the stage go through, and it disturbed the lake bed on the order of maybe twice as high as this room. Well, how do we go from that to this stuff on the surface? So first thing I'll say is, I think that, and we know now, that the sediment is very rich in phosphorus, particularly in certain areas. I also think, and the literature supports this, particularly with microcystins, and that previous chart described the prevalence of Microcystis aeruginosa, Microcystis botrys. They actually will live in sediment in a kind of suspended state over winter. They can last for years. And I think that's acting as a seed stock. So getting back to how does this plume that's 1 or 2 times the height of this room develop into a bloom, we started to notice that when the wind got strong, maybe about 4 meters per second, we started to see in the vertical velocity from the ADCP, we started to see this transition of water just going down and coming back up. Like, what's that? Well, it's Langmuir circulation. You may remember I told you, well, here's what it is. Langmuir circulation, if anybody doesn't know, it's these big coils of flow in the lake. So if the wind's going that way, these coils go like this, and they develop these windrows. I told you I was going to get back to that photograph. These rows of bubbles, this was on July 31st, these rows of bubbles are these windrows where stuff gets collected, where these helical coils come together. And what's really cool, this is, so we have north-south velocity. Yep. We have acoustic backscatter from 2 different frequency acoustic units. 600 kilohertz and 1200 kilohertz. Those frequencies have different acoustic wavelengths and reflect differently off of particulate in the lake. But what's great is that when these coils are going past us, we see in these windrows, they're sucking stuff down into the lake. This is cool as heck. And what's really cool, so you can see here, it's a little fuzzy, but this is the Langmuir circulation coming down here. Here the circulation is going all the way to the lake bed. This is called Langmuir supercells. And these supercells can actually, and we know this, we see this in our data, they can entrain material actually from the lake bed. But we know by the time that the HABS process has started, and I'll show you in a minute, we've already seen a disturbance in the bottom from the sage. So here's what we think the recipe is. Spoiler alert, strong south wind sets up the sage. The sage disturbs the bottom, Langmuir circulation follows, and then this recruited microcystis comes to the top. And it comes to the top on a calm day. So everybody's like, we get HABs when it's a calm day. Nobody remembers what the weather was last week or 2 weeks ago, or that we had a lot of wind maybe a week and a half ago. They remember the warm, calm day. That's when all this stuff can come to the top. So we have this recipe. let's see if it works. So there's a lot of stuff here. So we have wind speed, wind direction, north-south velocity. Again, these are the seiches coming through. They're coming through rapidly here. Anytime you see this yellow to blue or blue to yellow, it's a seiche coming through. Remember, we're only at one point in the lake, so we can only see what we can see. We have acoustic backscatter from 2 different frequencies, and we have vertical velocity. And by the way, these red dots are confirmed HABS days, so September 4th, 13th, and 16th. Okay, so here's some sage coming through, and we know, seeing the turbidity is coming up. Now that dotted line, Irving Langmuir, who discovered Langmuir circulation, he said 4 meters per second wind is generally the threshold for developing these coils. The development of the depth and the strength of them is dependent on wind speed beyond that and the duration of the wind. So that's why I have that dotted line. Well, lo and behold, here's some Langmuir circulation going right to the bottom. Calm day, we have a HAB. Well, here's some more sage coming through. We have elevated wind, and we have some Langmuir circulation. Calm day, HAB. Now this next one, I mentioned the August 4th, 5th, and 7th grouping of blooms in 2018. I consider them one. And I consider that one on the 16th to be an extension of the one on the 13th. What happened, we see a little bit of wind there, and you can't see it down there because of the zoom factor here. There's a little bit of Langmuir circulation a few meters down into the column. Calm day, another HAB because it hadn't run out of gas yet. Still nutrients available. And I want to mention another thing about this Langmuir circulation. Bottom gets disturbed with the seed stock and the nutrients. You're cycling this stuff. It takes about an hour in 18 meters where we were. It takes about an hour to go full circle. So all during the day, this recruited microcystis is eating, getting all kinds of exposure to light, and it's in warm water. So this is the HAB day. This is September 16th. Another cool thing about Langmuir circulation. Well, after the 16th, on the 17th, we see elevated winds. We see Langmuir circulation. We see stuff getting sucked down into the lake. What Langmuir circulation giveth, Langmuir circulation can taketh away. And it's sucking the HAB back down into the lake. Every time you read a news article, it says, well, HAB dissipated. What's that mean? I think at times, I think on the 4th, 5th, and 7th bloom, the HAB ran out of gas, died, and sank. I think on this bloom, it got sucked back down into the lake. So I said before, we can see what we can see with the sensor platform. Thankfully, that's not all we brought to the party. And I want to make the point that this is way more complicated than I just described for the following reason. I'm going to come back to this site. Everything, we were right here. We couldn't see down there. So how do we explain that? I'm going to come back to this. This little cartoon here is just that. Sage never looks like this. It is all wavy. At best, it looks like what I showed you for the first 2 weeks in August. Pretty regular low-frequency wave. But once you get energy coupling into that, that's either resonant or dissonant with that wave, you start to get wave packets, you get multiple waves, you get waves superposing into bigger waves and then disappearing. So from an observation perspective and a prediction perspective, how does that help us? So this is an animation from our three-dimensional physics-based hydrodynamic model. This was driven solely with our Deep Thunder weather model. Weather is being modeled at a 1 kilometer horizontal resolution, and it's being coupled into the lake surface at that resolution. At Lake George, we're doing that all on 3rd kilometer, so 9 times dense as this. And we're taking into account the regional topography of Lake George. I don't think we were here. This is the lakes. This is a piecewise planar view down the center of the lake. So this is the lake surface, epilimnion. This is, I believe, a 16-degree isotherm, essentially a thermocline, and hypolimnion. And so we're in late August, and we're kind of near the tail end of that regular slosh, and funky stuff starts to happen. Right? We've got a wave packet. We have multiple waves. We have something funky going on down here, and extreme stuff happening. I'll direct your attention. I'm going to come forward a bit. And the reason I'm showing this is because we had eyes right here. Even if we had 10 VPs down the lake, are we going to be able to see a lot of these subtleties? I'm not going to let this run through, but I have 2 still shots. September 11th, the thermocline is hugely distorted. And these vectors here are wind, so it's a strong south wind. This is the village down here. And that thermocline is so tilted that we're seeing, this is actually water speed. We're seeing the epilimnion like surfing down this wave here. And what's cool, right? Remember that halve on the 13th was right here. Look at this. It's way more energetic along the east shore than it is on the west shore. So that's on the 11th. On the 12th, this is actually a different wave. The next day, same deal. West shore, the water's less than 100 millimeters per second. On the east shore, 200 plus millimeters per second. And there just happens to be a shelf in the bathymetry on the east shore there. So that fits into our working theory that it's the Seiche and then the Langer's circulation inducing the bloom. This is another visualization. This gets back to the diffusivity on the lake bottom. So it's August 18th, 17th, through I think September 17th. So this is it's essentially the turbulence everywhere on the lake bottom. And it's hot up there, it's hot down here, but remember, this is steeper down here than it is up there. There's nothing in here that indicates bottom type. If I remember correctly, this is very steep and there's some bedrock down there. Up there, it's much shallower. And we can see even where we were deployed, we can see that hotspot. When we get to, this I'll fast forward if I'm able to that September 11th and 12th. And so keep an eye on this area here as well as the north end. Remember we had blooms on the 13th and 16th, really the 13th. So we're still on the 9th. A lot of activity up north. All right, so we're coming up, and you can start to see some action there, and you can see the wave. Here you go, bright yellow on the 11th. When remember that red.
I'm sorry, I'm trying to follow you, and what is it that we're looking at?
This is essentially turbulence at the lake bed.
How do you have this?
This is from a 3-dimensional hydrodynamic physics-based model. So it's running Navier-Stokes differential equations on a 3-dimensional grid. And it's
so what is the hot spot?
The hot spots would be turbulence at the lake bed, either water speed or something like the gradient of the thermocline transitioning over the lake bed. So just to, Professor George Bach said all models are wrong, some are useful. I would categorize our models as being in the latter category. This model is constrained by the fact that we're not running our highest resolution weather, we're not taking into account topography. You can see the bathymetry is quite crude. But still, 4 o'clock in the morning one time, I see this in the data. This is a very rapid upwelling and then downwelling of water for minutes. So I go to the model, and I'm literally frame by frame. The model time step is 10 minutes. I find this frame, and I see that as this SAISH is coming in, there's a wave front that's pushing water up. And I love this comparison here because it's a testament to how accurate this model is, even with the constraints. So where are we at here? Well, we think we've identified a fundamental mechanism of causality. I didn't show this, I showed this back in 2018. Using a very simple detection method on near surface phycocyanin out at our deployment location, we discovered, or we found every bloom. And then the physics-based modeling, I think, this is my last slide. This is really, what do you want to do? This is, if you want to detect, then you can put 1,000 phycocyanin sensors around the lake. If you want to predict, we have prediction algorithms based on primarily actually acoustic backscatter. I didn't show, actually I'm going to go back just a couple slides. I want to show one other thing regarding the line mirror circulation. So what we see here, they're both good examples. When the line mirror circulation starts to do this, look at what's happening in this acoustic backscatter. It's homogenizing the column. And then when it ends, and we have the calm day, it's recompressing. Same thing over here. This is the line mirror circulation. This is homogenizing the column. This is all that stew going through the water column, and then you get the calm day, and the buoyancy of the microcystis coming back up.
Can I just comment what you're measuring the backscatter?
Say again?
What are you measuring the backscatter? I understand it, but other people may not.
So we have two ADCPs. They're active sonar instruments, four transducers, instruments about this big. So they ping out acoustic energy, a sound, high frequency sound, and then they listen in time, which is the return through the different depths. And they can, through the Doppler effect, they can calculate flow, which is how we get that speed there. And then by virtue of the echo intensity, that we can tell the density of stuff that was in the water. Could be bubbles, could be microcystis colonies, could be dirt. The two frequencies, 1200 kilohertz really reflects ideally off of something on the order of maybe 1 to 2 millimeters, and 600 kilohertz, maybe 2 to 4 millimeters. So we coupled these observations. So these are acoustic reflectivity. We look at those with regard to turbidity, which is optical reflectivity. And that's what I showed early on. I'm just going to go back there. That's why I had this comparison here. So this is optical reflectivity in the way of turbidity, and then this is acoustic reflectivity, which is that backscatter, that intensity of the echo, normalized for depth and other operational environmental parameters. So, any questions?